Let's talk about sound waves. Sound waves are actually very kind of strange things to go through and think about how they work. And part of the reason for that is they're associated with really small displacements of lots and lots and lots of atoms and molecules that go back and forth many times per second. So we need to think very carefully about how they work. Now, what I'm going to do is I'm going to create a sound pulse. And I'm going to do that by dropping this book on the table. So there we had a loud thud, right? So what happened? Why was there a sound wave? Well, let's go ahead and look at what happened with the book as it was falling towards the table. So here's the book falling down towards the table. And what I've done is I've drawn little dots at locations of molecules inside the table. All right. Now, the molecules inside the table aren't really bothered until the until the book comes into contact with the table. Now, at that point, the book is moving down, but the table's in the way. So the table got to stop it, but it can't stop it instantaneously because that would require an infinite amount of force. The acceleration would go to infinity. So what the table has to do is deform itself a little bit. Now, of course, I greatly exaggerated this here, but you get the feel for it. All right. When it deforms itself, the atoms in the top layer become closer to each other. Now, down here, it's not really affected, but right here, look what we've got. A condensation. So we've got a nice little condensation of our molecules right here, and they don't want to be that close together. So they're going to fight that. They're going to try to push apart. And that means that the table is representing a medium for the propagation of a wave. And that wave is going to be a sound wave. Now, here we've got the molecules very close together. So that's associated with a displacement wave. Now, these molecules here are going to move out that way in order to get away from the other molecules. So the wave is moving this way, and the molecules are moving this way. So that means that this sound wave is a longitudinal wave. The displacement of the atoms and molecules is along the direction that the wave is moving in. All right. Now, so we definitely got a displacement wave here. But look here. We've also got these molecules that are close to each other here, and we can say that that leads to a high pressure zone. Now, as they push out, this table is going to reform itself, not going to be deformed anymore, and then I'm going to have a low pressure zone there. So I'm going to have both a displacement wave and a pressure wave. And that's what makes a sound wave. You have a pressure wave and a displacement wave. All right, now let's see a little bit more clearly how this works. So what I've got here is I've got my displacement wave plotted as a function of position. So here the displacement is maximum positive, here the displacement is 0, and here the displacement is maximum negative. All right, now this is a little bit difficult to understand how it works the first time you see it. So what I've done here is I've drawn a column of air. The black lines represent where the molecules are supposed to be. These are equally spaced because in equilibrium, they're supposed to be equally spaced. They're not supposed to be closer at some points and further away at others. Now, maximum displacement. That means that the molecules that are supposed to be at this black line right here are actually at the red line here. They're moved over the maximum amount in the positive direction. Now, as we go along here, we have them moved over less and less and less. As we start moving down here, they start moving backwards. So notice what happens. Here, everybody's moved over the same amount. So that means that nobody's closer together than they ought to be. They're just kind of all moved over. But look what's happening around here. The atoms on this side are moved to the right, and the atoms on this side are moved to the left. And so we've got this region right here where the red lines are closer together than they're supposed to be. So this is my condensation. Now, as we continue to go, here we've got maximum displacement, but in the negative direction. So again, it's like everybody just sat there and was just moved over the same amount. So it doesn't matter. It's the same pressure. Nobody cares. But then as we keep on going, once we get to this point right here, all the guys on this side are moved to the left, and all the guys on this side are moved to the right. So that means that we've got this area right here of rarefaction, low pressure. So if I were to graph the pressure wave, what I would end up with is zero pressure here, just because it's the same. And then as I go, we've got maximum pressure at the condensation, and then minimum pressure here at the rarefaction, and then back up. So if we compare the pressure wave with the displacement wave, we see that we took the displacement wave and we just kind of moved it over to the right 90 degrees. So the pressure and displacement wave that we talked about over here with the sound wave are 90 degrees out of phase. And this will be very important to us when we discuss standing waves associated with sound. Now, as far as most of the problems that I've seen about sound waves go, they're really just associated with this formula right here, V equal F lambda. And we know that one. That's standard for basically all waves. The only thing we need to know is what's the speed of sound. Well, in air, at standard temperature and pressure, so that's 0 degrees Celsius, 1 atmosphere of pressure, the speed of sound is 331 meters per second. So if they give me the wavelength, I know the speed, I'll divide and that'll give me the frequency. At 20 degrees Celsius, which is more like room temperature, again, 1 atmosphere pressure, the speed of sound is 343 meters per second. Again, same thing. So most of the time in these problems, they'll say, the temperature is this. Here's the frequency. What's the wavelength? All right? And that's sound waves.